Alright, so this is the first video for Unit 6, which covers Chapter 14 of your textbook. And the first part of it is going to be on equilibrium and oscillations. So, if you can think of a marble that's rolling on like a U-shaped track, it's just going to roll back and forth. It just keeps going down and up and down and up and down and up. The equilibrium position where the forces acting on it are at the bottom. At that point, the weight going down and the normal force going up would be equal and opposite. Okay. So if we push it up, there's a force that's going to act at an angle to want to drag the ball back down to its equilibrium position. And that force, which in terms of the marble is this F net here, is called your restoring force. That's your net force acting on the marble to bring it down to the equilibrium position. So when the marble is released from side to side, it does not stop at the bottom. It rolls up and down. This is called an oscillation. So the ball rolls back and forth and back and forth. It oscillates back and forth. And any oscillation can be characterized by something called the period and the frequency of an object. So for any oscillation, the time it takes to complete one cycle is called the period. So if we go back to the marble example, the time it would take the marble to go down, back, down, and then return back to where it started, that whole time period would be the period of the oscillation. So there and back is one complete oscillation. And the number of cycles per second is called the frequency. So again, if it went there and back in 1 second, the frequency would be 1 wave per second, or the unit is 1 hertz. Okay. So period is the time it takes to complete a cycle. Frequency is the number of cycles in a given amount of time. And they are inversely related. So as the period goes up, the frequency goes down. So if you have a greater period, your frequency is going to decrease. They're not going to be made as frequently. Common uses, you probably, if you listen to like radio stations, they're in megahertz. Okay. Really big frequency, really little period, because as one goes up, the other goes down. So radio station broadcasts at 100 megahertz. What's the period? So they're inversely related. So the frequency, the period is 1 over the frequency. We know the frequency is 100 megahertz. Mega is 10 to the 8th. So you have 1 divided by 10 to the 8th, which is 10 to the negative 8 seconds, which is actually 10 nanoseconds. So the graph of an oscillation motion, if you're looking at like position like this one, is a cosine function. And if we were to graph it, it would make a sinusoidal function. So this whole function here, this sinusoidal function, shows what's called simple harmonic motion. We look at the position versus time graph of this object, and it makes a sinusoidal curve. So we have this motion. If we graph the motion of this pendulum, the position versus time, it would make the same sinusoidal function, where this bottom part, the resting position, is your 0. So the graph would make that same sinusoidal function. So the two main types of oscillating motion that we're actually going to look at in this particular unit are springs and pendulums. So springs they bounce back and forth. You put a mass on a spring and you make it bounce either sideways or up and down. Okay, so that mass oscillates back and forth due to a restoring force on the spring, and the period depends on the mass and the stiffness of the spring. The other one is a pendulum, like we just showed you in that simulation. The mass oscillates back and forth due to the restoring gravitational force. The period depends on the length of the pendulum and the free fall acceleration. It doesn't depend on the mass at all. Examples. So like a mass restoring force, the type of example you can think of is like your eardrum vibrating, the inner part of your ear, not just your eardrum, but the inner part of your ear undergoing vibrations due to energy hitting it at different rates. And pendulums are just walking like legs. Okay, if you can actually walk straight-legged, you will swing your leg like a pendulum. All right, so now we talked a little bit about the restoring forces, especially here. So the restoring force pulling in the spring or the mass back into the resting position of the spring, or the restoring force pulling that pendulum back down to the bottom. But now let's really look at what the linear restoring forces. Okay, so if you look at a spring, so if you displace a spring, the spring exerts a restoring force back towards the equilibrium, and the negative sign tells us that it's a restoring force because the force is going to be negative. So if I apply a force, and we look at the vectors here, so if I apply a 1 Newton force, or a 20 Newton force, okay, so my applied force is that way. I have the spring force is actually pulling it back the other direction. Okay, so the restoring force in this one is actually the spring force. Now, if the applied force gets pushed this way, now the restoring force is the blue. The restoring force wants to take it back to its normal position, to its resting position. And this is simply just Hooke's law. Force equals spring constant times your displacement. So this is a linear restoring force, the force that wants to take it back to its resting position. So amplitude is how far you pull it, and it's going to again make a sinusoidal curve. If you look at the amplitude versus the middle part is your equilibrium resting position. So if the object could bounce back and forth, it would make the sinusoidal curve. Much like the pendulum does. So you could figure out your amplitude, the distance of maximum displacement. And because this is your time interval, if you go from point A to point A and point negative A to point negative A, those time intervals between those are the same. And that time interval from this point to this point is your period. So for the hanging weight, the equilibrium position of the block is where it hangs motionless. So where the spring force pulling up equals weight going down. So if I apply a force and it bounces, and I take it into slow-mo here, I can find a spot if I measure. There's our maximum stretch right here at the bottom. And there's my maximum displacement, my maximum squish, compression. My equilibrium position will be right in the middle of that. So we've got a 30 centimeters from my minimum displacement to maximum displacement. So that means my equilibrium position is in the middle. So right about there. And this oscillates every time it keeps the same oscillation height. Okay, so again from Hooke's law we get the spring force is equal to the spring constant times the length of the spring. Newton's first law from the block, the net force the net force will keep something moving at a constant speed. So the force, the spring force plus the weight is equal to the spring constant minus the mass of the gravity, mass times gravity. So this takes into account the spring minus the weight, and at equilibrium, the net force would be 0. Because at equilibrium, the spring force pulling up is equal to the weight pulling down. So that means if the spring force minus the weight is 0, that means the spring force needs to equal the weight. So you can rearrange it to solve that the length is mass times gravity divided by your spring constant. And you can rearrange this to find other things too. You could rearrange this to find the spring constant if you knew how the length of it. And you knew the mass of the weight that was pulling the string, or the spring. So when the block is above the equilibrium position, the spring is still stretched by an amount of L minus Y. So this. So now the net force on the block is at the very top. You're actually going to add those two together. Okay, so F net at the top, where its block is above the position, F net is equal to negative Ky. Because negative, it's going upwards, away, it's going the way that the spring doesn't want it to go. Because the spring is getting stretched, or excuse me, the spring is getting squished, and it's going to push it, wants to push in an opposite direction. So the role of gravity is to determine what the equilibrium position is, but does not affect the restoring force for displacement, because it has a linear restoring force. A mass on the vertical spring oscillates. So that means that this really the only force, the restoring force, is all due to the spring constant. It's all, the thing that changes that is the spring constant, not necessarily the force of gravity. All right, so we've got this problem here. The biggest place you're going to see springs is in your vehicles. Your cars have springs all over them. The main ones are on your tires, your suspension. And each spring supports approximately 1/4 of the weight, the mass of the vehicle. A lightweight car has a mass of 2,400 pounds. When a 160-pound person sits in the left front fender, this corner of the car dips about 1/2 inch. What's the spring constant of the spring? And when 4 people this mass are in the car, what's the oscillation frequency of the vehicle? Wow, that's a good FRQ question. So here we go. So if we use Hooke's law, the force equals spring constant times your displacement. The displacement on the spring is 1/2 inch when subjected to force of 160 pounds. The spring constant then is 160 divided by 0.5 pounds per inch. Convert this to Newton meters, you get K is 710 newtons divided by 0.031, or you get a spring constant of 5.5 times 10 to the 4th. You can use to do this, a newton is about 1/4 pound, and there's 3 centimeters in an inch, so you can use that conversion, right? So the frequency of the oscillation is the square root of the spring constant divided by the mass. So each person behaves the same way, so you consider one spring with a mass, or one person with a mass of 160 pounds, which is 73 kilograms, plus 1/4 of the car's mass. So 600 pounds implies a mass of 270 kilograms. So the total mass is 340. I'm going to have you skip part B for right now, because part B does not actually, you don't have the formula for it. Because you're probably, if you pause, you're like, wait, what? We don't have that. That'll be explained later. The last bit of this is looking at the restoring force on a pendulum. So the pendulum is basically just a mass on a string that pivots. The string pivots at a point, and the pendulum goes back and forth. The weight at the bottom is called the bob. The mass moves along a circular arc. The net force is the tangent component of the weight. So if we look at this, So here's our free body diagram. We have the weight pulling down. We have it at a certain angle that we've pulled it. So this is the angle that the string has been pulled from the resting position, which means you have a tension from the string. You have the weight of the bob pulling down. This force right here, that is your restoring force. That's the force that's pulling the bob back to the equilibrium resting position. And if you think about that, so you have your angle. If you have the mass of this, you can have the weight. So your restoring force then is the weight times the sine of theta. Because it's the opposite side of the angle that you know. Weight times the sine of theta gets you this restoring force side. This only really does apply for angles that are really small. So the force net is mass times gravity times sine of theta. And because these angles are really, really small, the sine of theta is about theta. And so then you can have S over L. So the force net is mass times gravity divided by the length times your arc. S is your arc length. So if you know the arc length that you pulled it back, and you know the length of the spring, or the length of the pendulum string here, mass times gravity times the length of the string, times how far you pull it back, your arc length, that'll get you your net force. And this thing undergoes simple harmonic motion. So if you kind of think about it, as this gets lower and lower, 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 the restoring force decreases. Right here, at the very bottom, there is no restoring force. Because at the very bottom, you have equilibrium, where the weight balances the tension. Okay, so that's the end of the first video. Answer the questions on the Google form. And if you have any questions, please ask. We'll talk to you soon.